Hi, welcome to Chapter 6, Electron Structure of the Atom, Part 3, where we're going to talk about quantum numbers and orbitals. So the first thing we need to start with is, what is an atomic orbital? So you see here in this picture, the propellers of the plane are whirling around, and you can't really tell where the propellers are, but you know the area they reside in. You know they are somewhere in this area. And it's the same thing with our electron. We can't tell exactly where our electron is located at any given point, but we know where it likes to spend most of its time. So the probability of finding an electron in an atom, you can visualize it by fuzzy clouds, and we call these our atomic orbitals. So what is our atomic orbital? It's a region of space where you have a high probability of finding the electron. I also like to say it's the path the electron takes. Okay, the path the electron takes. Now this electron is taking this path in an energy level. Energy levels are represented by the quantum number, principal quantum number, which is represented with n. And n is a integer that starts at 1 and can go on. It's related to the rings in the Bohr diagram, where n is 1, 2, 3. So as you move out, your n value is increasing. It's also related to the periods on the periodic table, where the first row is n equals 1, the second is n equals 2. So how did this all come about? Well, our last video we talked about de Broglie and Heisenberg's principle, and then Schrödinger took it a step further, and he used something that we now know or call quantum mechanics, and he did some powerful math, and he came up with this wave function for the electrons. And he came up with an equation, a wave equation, that's represented with this Greek psi symbol. And if he took the square of that function, it gave you the electron density, which basically tells you the probability of where an electron will likely be at a given time. And here is a plot of one of his wave functions. And you see the dots are more dense here, so there is a higher probability of finding your electron here. Than as you move out, the probability decreases. And if you look at this and think about it in 3 dimensions, what kind of shape does this look like? Well, it looks like a sphere. Okay, and this is one of the sublevels or shapes we're going to talk about in a minute. So there are 4 quantum numbers, and in order to describe your orbital, remember the path that the electron is taking, you only need 3 of them. You need your principal quantum number, which we just said is your energy level. You need your angular momentum quantum number, which describes the shape of the sublevel. And you need your magnetic quantum number, which kind of gives you its orientation in 3 dimensions. If you want to pinpoint where an electron spends most of its time, you'll need the 4th quantum number, which is the spin quantum number. So let's talk about our principal quantum number. Again, it's designated with the letter n. It can range from 1 to really any value, but if you look at our periodic table, it goes up to 7 periods, so that's the highest for the elements here on Earth. It corresponds to the rings in the Bohr model, and it is related to the radius of the electron cloud. So as n increases, you are further away from the nucleus. Also, as n increases, your energy levels are higher energy. So again, as n increases, higher energy, and further away from the nucleus. Your angular momentum quantum number, I said, helps describe the shape of the sublevels. So sublevels are within your energy level, and there are 4 of them that we're going to talk about, and they each have a different shape. We already saw the first one, which is the S, which looks like a sphere. Okay, the letter we use to represent this is L, and the values for L can range from 0 to n-1. Okay, I always like to say it was like a decoder. So you know what sublevel you're in, the S to P to D to F, and you use these numbers right here to represent your L value. And if I needed to rank the energies of my sublevels, you start at S, which is the lowest, and you go up to F, which is the highest. So if n equals 2, what is the value of L? Remember, L ranges from 0 to n-1. So if n is 2, L could be 0 or 1. So you could have an S and a P sublevel. So here are the shapes of your sublevels. Where S is spherical, and here's the image of it. And there's only one path within the S orbital, one orbital in there. Because no matter how you look at a sphere, from the x-axis, the y, or the z, it always looks the same. Okay? Then you have your P, which we like to say looks like a peanut or a dumbbell. And there's 3 ways you could orient it. On the x-axis, the y-axis, or the z. Okay, it has 2 lobes. These are called lobes right here, lobes. And it has 1 node. Right here is the node, right in the middle. In the node, there is a 0 probability of finding an electron. That's what a node is. Then you have the D, which looks like, here's the D's down here. They look like 4-leaf clovers, and they are each oriented on the different axes. And then the last one looks a little weird. And this one they kind of call a donut because of this ring here. Okay? So there are 5 D's, 3 P's, and 1 S's. And the last one is the F, which is very complicated. And there are 7 of those orbitals. Here is a picture of it, and you can see how it could get very confusing. They don't even have a picture of it in your book. I had to get that off the web. So let's zoom in on the S orbitals. Here we have, on this top graph, probability versus distance from the nucleus. So your 1s has a very high probability of being nice and close to the nucleus. Okay? Your 2s, notice where there is a higher probability, a little bit further from the nucleus. So as this number increases, that is your n, right? You are getting further away from the nucleus, and we said that previously. Here is n equals 3, and you see here is where you have the greatest probability of finding your electron. Now notice, as n increases, you get more of these nodes. So when n equals 1, there is no node. When n equals 2, there's 1 node. When n equals 3, there's 2 nodes. So the nodes are n-1. Remember, a node is a probability of 0. So electrons will not reside in that area. Okay, so as n increases, you're getting further away from the nucleus, and your energy is increasing. So how are sublevels, which are our L's, related to our principal quantum number, which is our N's? Well, as it turns out, your principal quantum number tells you how many sublevels you will have. So look here, when n is 1, you have one sublevel, and it's called the 1s, where the number here is n. And there's always one orbital within your s, because remember your s, no matter how you draw it, it always looks like a sphere. When n equals 2, you could have an s and a p. So we're always starting at our low energy and then working our way up. Okay, remember S has one orbital, P has 3, D has 5, and F has 7. So when n equals 3, you could have 3s, 3p, and 3d. And when n equals 4, you could have 4s, 4p, 4d, and 4f. Now, your magnetic quantum number, which is represented with this m sub l, it describes the orbital within a sublevel. So what am I talking about? Well, let's take S. That's the easiest one. S only has one orbital. So we'll draw it like this. So we label that 0. So that would be our ml value. P has 3 orbitals. And we need to give them some sort of label. So your ml ranges from negative L to positive L. So remember, if you have a P, your L is 1, so it ranges from negative 1 to positive 1. Okay, if you have a D, L value is 2. You have 5 orbitals, so it'll range from negative 2 to positive 2. And finally, F has 7. So on and so forth. And that's what they're showing you here. This is for the S, and they're saying it's 0. Here's for your P. There's 3 of them. I always like to start with a negative and work my way positive. So on and so forth. So remember, if you know your L, your ml is equal to negative L to positive L. Now, a couple slides ago, we talked about hydrogen. Hydrogen has 1 electron. Because it has 1 electron, there are no electron repulsion forces. If you have electron repulsions, you actually end up increasing the energy of your orbitals. So since there's only 1 electron, and it's not really interacting with anybody else, you notice when n equals 1, everything here has the same energy. And when n equals 2, everything on the 2 has the same energy. And when n equals 3, all of these have the same energy. That is called degenerate orbitals. They have the same energy. Now, when you have many electrons, you're going to have repulsions. And repulsions increase energy. So here's your n equals 1, but notice your n equals 2. Your P is higher energy than your S. And n equals 3. S, then P, then D. So here, your energies, again, this is your lowest to your highest energy. What's interesting is within a sublevel, so if you're in the same sublevel, they have the same energy, right? All of these have the same energy. So how many electrons can we fit on our principal energy level? Remember, that is n. So let's think about it. If n equals 1, that means L equals 0. which is S. And there's only one orbital in S. And an orbital can hold 2 electrons. So when n equals 1, you have 2 electrons. When n equals 2, L could be 0 or 1. So you have a 2s and a 2p. Remember, p has 3 orbitals. Each orbital can hold 2 electrons. So here you have your 2s2s and your 2p6s. That holds, when you add these together, 2 plus 6, 8 electrons. When n equals 3, your L could be 0, 1, or 2. So you have your 3s, your 3p, and now your 3d, which has 5 orbitals. So what do you have? You have 3s with 2 electrons, 3p with 6 electrons, and 3d with 10 electrons. When you add that up, it's 18. Now we could keep doing this, or we could just use the relationship 2n squared, where n is your principal energy level. So let's say n is 5. What is 5 squared? 25, and 2 times that means it could hold 50 electrons. Now, in the previous slide, if you notice, when I was filling my orbitals, I was drawing like these half arrows. One was pointing up and one was pointing down. Since you have 2 electrons in one orbital, they have to spin in opposite directions. And we call the up arrow plus a half, and the down arrow minus a half. And it's not really a full arrow, it's like a half arrow. Okay, you can't have 2 electrons in the same orbital spinning in the same direction. And that's it for part 3.